Welcome to lecture 9 on measure and integration. As you recall, we have been looking at classes of subsets of a set X called semi-algebra, algebra, sigma algebra and so on. And then we also looked at set functions defined on these classes with properties. So, in particular we defined the concept of a measure. A measure is a set function defined on a collection of subsets such that the measure of mu of the empty set is equal to 0 and mu is countably additive. Today, we are going to start the process which is called extension process. So, the topic for today's discussion is going to be extensions of measures. Basically, the question arises from some properties on the real line. Let us look at mathematically the question. We know that notion of length is defined for all intervals. So, the question is, can the notion of length be extended to arbitrary subsets of the real line? That means, can we define the notion of the length for an arbitrary subset of the real line? Of course, it should be compatible with the definition of the length for the interval. So, the need for such an extension, one of course, is purely a mathematical curiosity that we have the notion of length for an interval, can we define it for a arbitrary subset. Another reason which is more important is that it arises from some problems in Riemann integration. The concept of Riemann integral, which is defined for a class of functions, fails to satisfy some nice properties, like if a function is the fundamental theorem of calculus does not hold for Riemann integrable functions. So, in order to remove those difficulties, one started for looking for an extension of Riemann integral, and that led to the problem of extending the notion of length from a class of subsets, that is intervals, to all subsets if possible. And if you are interested in looking at more details about that, why Riemann integral should be extended to a wider class of functions and how that leads to the concept of extending the notion of length to arbitrary subsets, read chapter 1 and 2 of the textbook that we have mentioned earlier, namely an introduction to measure and integration by myself Inder Kerana. So, let us start with the question of what is an extension. So, let C 1 and C 2 be two classes of subsets of a set X, and let us assume C 1 is a subset of C 2. We have two measures or two set functions mu 1 and mu 2. Mu 1 is defined on C 1 and mu 2 is defined on the collection C 2. So, mu 1 and mu 2 are set functions, mu 1 defined on C 1 and mu 2 defined on C 2, with the property that mu 1 on C 1 is same as mu 2 for subsets of C 1. So, mu 1 and mu 2 agree on subsets of C 1. Recall C 1 is a sub collection of C 2. So, in such a case we call mu 2 is an extension of mu 1. So, on C 1, which is a smaller class, mu 1 and mu 2 are same. So, and mu 2 is defined on a bigger class, that is C 2. So, we say C 2 mu 2 is an extension of the measure of the set function C 1. So, the problem is, given a measure mu, we start with a measure mu on a semi-algebra C of subsets of a set X. We want to show that there exists a unique extension to a measure mu tilde on A of C, the algebra generated by it. So, this is going to be our first step of extension theory, namely given a measure on a semi-algebra, we are going to extend it to a measure on the algebra generated by that semi-algebra. So, let us see how this process is carried over. So, recall that a set E in the algebra generated by a semi-algebra, we had characterized such sets, can be given by a representation E is equal to union I 1 to n E I, So, every set in the algebra generated by semi algebra is a finite union of sets from the semi algebra, and in addition they are pairwise disjoint. So, this was the result we had proved, that the algebra generated by semi algebra is nothing but all finite disjoint union of sets in the semi algebra. So, let us take any set E in the semi algebra. So, we define mu tilde of E to be sigma I 1 to n mu of E I, and the claim is that this is the unique extension which we are looking for. So, let us see how do we do it. So, we have got mu on C, and this is a semi algebra. So, we define mu tilde on the algebra generated by C. So, this is algebra generated by C. So, we want to define a function here, a set function which should look like an extension. So, if E belongs to f of C, then we know this set E looks like a disjoint union of elements C I equal to 1 to n for some n, C I belonging to C. Now, why we defined it the way we have defined mu tilde? See, if mu tilde of E is going to be defined and it is going to be a measure on the algebra f of C, then we know that every measure is also finitely additive. So, by the finite additivity property of mu tilde, which we have not yet defined, but the finite additivity property will say that this should be equal to mu tilde of the union C I equal to 1 to n, and this being finitely additive, we should have I equal to 1 to n mu tilde of C I. But mu tilde is going to be an extension. So, that means mu tilde on C i's is same as mu on C i's. So, this is same as 1 to n of mu of C I. So, that actually fixes what is going to be the definition of mu tilde of E. So, if E is a finite disjoint union of elements which is C i's, then mu tilde of E must be given by this, and that also shows the uniqueness of the definition of mu tilde. So, mu tilde should be defined by this, it is necessary, and we will show that actually this definition works also. So, let us prove this property, that mu tilde. So, first we want to show that mu tilde is well defined. So, what does that mean? So, suppose E is a set which is in f of C, then we know that E can be written as a finite union of sets C i's, finite disjoint union of sets C I in C. But it is possible it can have some other representation. So, it is possible there is also representable as j equal to 1 to m of some sets d I, where C i's belong to C and d j's also belong to C. So, to show then, because our definition depended on the representation, so we should show that mu of C I summation I equal to 1 to n is same as summation mu of d j equal to 1 to m. So, this is we should show, then only we can claim, if we are able to show this, then only we can claim that our function mu tilde is well defined. So, let us show this. So, now note, because E is given by these two different representations. So, I can write union C I equal to 1 to n also as union C I intersection union d j's, j equal to 1 to m, right. So, that is equal to sigma, that is equal to union I equal to 1 to n union j equal to 1 to m C I intersection D j. And similarly, union D j's j equal to 1 to m is also representable by the same way, because the two sets are same. So, it is the same representation, right. So, now let us compute. So, let us compute sigma mu of C I equal to 1 to n. I can write it as sigma I equal to 1 to n. Now, this mu of C I is the disjoint union of C I intersection D j, that is where we are using this representation that we just now wrote, j equal to 1 to m. And this is a disjoint union. C i's belong to the semi algebra, D j's belong to the semi algebra. So, this intersection belongs to the semi algebra, and their unions is C I, which is also in the semi algebra, and mu is a measure on the semi algebra. So, this is also finitely additive. So, it is I equal to 1 to n. So, I can write this sigma equal to j equal to 1 to m mu of C I intersection D j. Similarly, we can also write j equal to 1 to m mu of D j to be equal to, this is summation j equal to 1 to m, and mu of D j. So, that I can write as union of D j intersection C I equal to 1 to n. And now, again by finite additivity property, this is j equal to 1 to m sigma I equal to 1 to n mu of D j intersection C I. So, look at this equation 1, look at this equation 2, 1 and 2 imply that sigma I equal to 1 to n mu of C I is equal to sigma j equal to 1 to m mu of D j. So, that says, so implies mu is well defined. So, what we have shown is the following, that we take any set in the algebra generated by the semi algebra. So, that has got a representation in terms of the elements of the semi algebra. So, any element E in the algebra generated by the semi algebra can be represented as a finite disjoint union of elements in the semi algebra, say C I. So, pick up any such representation and define mu tilde of E to be equal to sum of mu's of these pieces C I, sigma I equal to 1 to n. It does not matter which representation you choose, you will always get the same sum. So, that means mu tilde of E is well defined. So, now let us look at the next property, namely that mu tilde, which is defined on the algebra generated by the semi algebra, is finitely additive. So, let us prove that property. So, we want to prove that mu tilde, so mu tilde is finitely additive. So, to prove that, what we have to show? So, let E be written as a union of E j's, j equal to 1 to n, where each E j belongs to the algebra generated by C, and of course, E also belongs to the algebra generated by C, right. So, we want to show that E mu tilde of E is equal to summation j equal to 1 to n mu tilde of E j. So, this is what is to be shown. Now, to show any such property, we have to go back to the definition of mu tilde of any set. So, since E belongs to the algebra generated by C, that implies, let us write each E j. E j belongs to the algebra. So, each E j can be written as a disjoint union of E j and say k equal to 1 to n j. where E, J, K belong to C for every j and k. So, every element E j is in the algebra generated by C. So, it must be a finite disjoint union of elements of C. So, that implies that the union E j equal to 1 to n is equal to union j equal to 1 to n union k equal to 1 to n j of E j k, and this is my our set E. E is equal to union. So, we have represented E as a finite disjoint union of elements of C. So, that implies that mu of E mu tilde of E, I can choose any representation. So, in particular this. So, it is equal to summation j equal to 1 to n summation k equal to 1 to n j of mu of E k j. And now, using the finite additive property of mu, we will write this. So, this is equal to look at this sum. So, look at this sum, okay. That is nothing but j equal to 1 to n mu tilde of E j, right. That is by definition, because E j is a union of E k j over k. So, by definition I can take that representation and write this is equal to this. So, that says mu tilde of E is equal to this. So, hence mu tilde is finitely additive. So, we have proved that mu tilde is finitely additive, and uniqueness we have already shown. So, thus we have shown that a measure which is defined on a semi algebra can be in a unique way extended to the algebra generated by it. And basically the idea is, because every element intuitively keep in your mind that mu of a set is the size. So, any element in the algebra generated by the semi algebra is a union of disjoint pieces in the semi algebra, and size of each of them is known. So, the size of the union must be equal to sum of the sizes of the individual pieces, because they are disjoint. So, that was the idea, and that helped us to extend a measure from a semi algebra to the algebra generated by it. So, that is the first step of the extension theory. So, as a consequence, the length function can be extended, that we have already shown. Length function can be extended from the collection of all intervals to the collection of finite disjoint union of intervals, that is the algebra generated by it, right. So, now we will go to the next step of the extension. So, we will start with a measure which is defined on a algebra, and we want to try to extend it to the sigma algebra generated by it. So, the next step in the extension theory is going to be, can the length function, for example, we would like to say, can the length function be extended to all subsets of the real line. We have done it from intervals to the algebra generated by intervals, right. There is a theorem by a mathematician called S. M. Ulam, and that theorem was proved in 1930. It says that under the assumption of continuum hypothesis, it is not possible to extend the notion of length to all subsets of real line. And this is a very important theorem. So, it uses two things, namely one is what is called continuum hypothesis. I will not go into the discussion of what is called continuum hypothesis at this stage. I would stress that one should read about this theorem from the text that we have just now mentioned, an introduction to measure and integration. So, this is a very nice and important theorem, which says as a consequence that it is not possible to extend the length function to all subsets of real line. So, the question comes, if we can't extend, so in general given a measure mu on an algebra of subsets of x, we would like to extend it to a bigger class than A. It can't be done it for all subsets anyway, but let us try to intuitively follow our idea of measuring the size of an object. So, intuitively, given a measure mu on an algebra A, a collection of subsets of a set A of a set X, mu of A is the size of the set A which you can measure, and given an arbitrary set E, one may not be able to measure its size exactly using the mu, but we can at least try to approximate, right. So, let us define what is called the outer measure induced by a measure. So, let us take mu an algebra of subsets of a set X, A an algebra of subsets of a set X, and mu a measure defined on it. For any subset E in X, let us define what is called mu star of E. So, what is mu star of E? What we do is, given the set E, so here is the set E, you cover it by sets AI's in the algebra. You cover it by the sets in the algebra. Okay. Take a covering of E by the sets AI's in the algebra, and you know what is the size of the set AI. So, let us take the size of the set AI and add up all these sizes. So, what do you think this sum will represent? This sum will represent in some sense the approximate size of the set E. Of course, it depends on the covering AI. And now, what we do is, we take the infimum of all these approximate sizes. That means, we take the infimum of these numbers over all possible coverings of the set E, and define that number as mu star of E. And we will try to analyze what are the properties of this mu star of E. So, first of all, let us give it a name. This mu star of E is called the outer measure induced by mu. Why the outer? Because we are covering E, right, by sets. So, these things cover E. We are going, maybe we are going outside E. So, this is outer, and measure, because we are trying to measure the size of this in terms of induced by mu, because in terms of the known size is mu. So, once again let us recall and look at carefully what this mu star is. Given a set E, arbitrary subset in X, cover it by elements A I whose sizes you know. So, take a covering of E by elements in the algebra, look at the sizes of A I's, add up all this, that is the sum mu A I, that is the approximate size, and take the infimum of all these approximate sizes. So, that we are going to call as the outer measure induced by. So, the first property we want to say is mu star is well defined. Well, what is the meaning of mu star is well defined? So, let us go back to the definition. This is mu star is the infimum of some numbers, right, and infimum of a subset of numbers exists in the real line if it is non-empty and it should be bounded below. Of course, all these numbers are going to be bounded below, because all are non-negative numbers. So, it is bounded below by 0. Why is this non-empty? Why is this collection non-empty? Because A is an algebra. So, the whole space belongs to it. So, keep in mind A is an algebra, and in the definition of an algebra, the whole space X is an element. So, E is covered by X itself. So, and X belongs to the algebra. So, at least there is one number in this collection over which you are taking infimums, namely mu of X. So, it is a non-empty collection of extended real numbers. So, its infimum always exists, and hence mu is a well defined number. Of course, it could be equal to plus infinity. Keep in mind the numbers here, they are all extended real numbers. So, this set is a collection of non-negative extended real numbers, and their infimum always exists, and infimum could be equal to plus infinity. So, we have shown that mu tilde is mu star, the induced outer measure is well defined. The next property, so mu star is a well defined set function on the class of all subsets of the set X, and we want to show some properties of it. So, the first property is mu star of empty set is equal to 0. That is true because empty set belongs to the collection A in the algebra, and mu star of there is equal to mu of A, and that is equal to 0. And for any set, that is a infimum of non-negative numbers. So, this infimum has to be bigger than or equal to 0. So, that first property is obvious. Second property, we want to check that mu star is monotone. So, let us check that mu star is a monotone function. So, let us take let A and B be subsets of x and A subset of B. To show mu star of A is less than or equal to mu star of B. Now, what is mu star of A? This is in all these properties we are going to use the definition of infimum critically. So, what is mu star of A? Mu star of A is defined as, by our definition, it is the infimum over sigma mu of E i's, say 1 to infinity, where this set A is contained in union of E i's, disjoint union, and of course, E i's belong to the algebra, right. And what is mu star of B? That is the infimum I equal to 1 to infinity of mu of say f i's, where B is contained in union of f i's I equal to 1 to infinity, a disjoint union, where f i's also belong to the algebra A. Now, note, if A is given to be a subset of B, if A is subset of B and B is covered by F union j equal to say f 1 to infinity, then that implies A is also inside. So, this is also inside f of j. So, what we are saying is every covering of B is also a covering of A. So, and this is the infimum over all possible coverings of B, and this is the infimum over all possible coverings of A, and every covering of B is also a covering of A. So, here we are taking infimum over a larger set, and here we are looking at the infimum over a smaller collection of numbers. And whenever you take infimum over a smaller collection of numbers, that is always bigger than or equal to infimum over a larger collection of numbers. So, that is a simple property about infimums. If you are taking a infimum of a larger collection, then that tends to be smaller than the infimum over a smaller collection. So, that property implies that mu star of A has to be less than or equal to mu star of B. So, that is purely a property of the infimum over what collection you are taking. Every covering of B is also a covering of A. So, coverings of B form a subset of coverings of A, and hence this property is true. So, that is the monotone property, namely mu star is monotone. Let us look at the next property, namely mu star is countably subadditive. So, we want to prove mu star is countably subadditive. So, that means what? To show. So, what we have to show? That if A is a subset of x and A is contained in union of A i's, A I is also a subset of x, then we want to show that mu of A is less than or equal to summation mu of A i's. So, this is what is to be shown, right. Now, let us observe. So, note we want to show one number mu of a is less than or equal to sum of these numbers. If one of these numbers is equal to plus infinity, then obviously this property is true. So, note if mu of a I is plus infinity for some I, then clearly mu star of a is a number which is less than or equal to plus infinity, which is at least one of the mu a i's. So, that is less than or equal to mu of mu. So, this is everything about star. So, it is mu star we are looking. So, let us just write mu star. We are trying to prove that mu star is countable additive. So, mu star of a I equal to 1 to infinity. So, what we are saying is this inequality is obvious if one of the terms in this sum is equal to plus infinity. So, let us take the case when all of them are finite.